You would find it weird that when this happens, the moon just kind of sits in front of the sun for like half an hour.
Just chill.
Okay, so as many people are getting right away, don't look at the sun. It's a bad idea. So that's not the problem I had with this, though. I mean, you can kind of like look off the side, and I've actually looked directly at the sun through clouds and seen sunspots on it, and you're fine if it's thick enough clouds, but still don't try this unless you know what you're doing. But what bothered me is eclipses don't happen that fast. That took 30 seconds. A real eclipse takes much, much longer. So what? Kenshin just stood there for that long going, What I want to know is, okay, we're going to assume that Kenshin didn't do that. In an anime Kenshin world, the moon travels a lot faster. How can we make this work? So, starting off, a real eclipse, to go from not covering to covering to uncovering again, takes 2 hours. In anime land, I keep hitting the wrong buttons. It takes 1 minute. In other words, it moves 120 times as fast. So let's get some other variables we're going to need here. The real orbital period of the moon is about 29 days, 29 and a half. There's some other units to keep it in because we're probably going to be working with smaller units here since that one's moving so fast. So the orbital period of the anime moon is every 6 hours. It goes all the way around the Earth.
Whoops, every day.
Other variables we'll need here, we have the mass of the Earth is about 6 times 10 to the 24th kilograms. The mass of the moon is a little bit more than 100 times less massive. And the distance to the moon at perihelion means its closest approach. And when it's at its closest, it's moving its fastest. I'm trying to give it the best chance here. But its distance is going to be 3.63 times 10 to the 8 meters. Now, what we want to do with this is we want to play with Newton's revisions to Kepler's third law, which I have the equation here, which says that the period squared is directly related through some other variables to the distance cubed. So we can play with these variables. I can't change the distance because if the distance was different, then the moon wouldn't perfectly cover the sun like it does. I can't change the mass of the moon because then the Earth would be orbiting the moon and not the other way around. I can't change the gravitational constant because then the whole universe breaks. The only thing I can really play with here is the mass of the Earth. So, how massive does the Earth have to be to keep this moon in orbit at that speed? So, let's plug all these variables in after we've kind of solve our equation here. And plugging it in, we get that the Earth has to weigh 1.33 times 10 to the 33rd kilograms. Let's put that in context, because not everyone here speaks scientific notation. We can calculate the surface gravity from this little equation here. Again, we just calculated the new mass. The radius is going to be the same. And so we get that the surface gravity is going to be 2.2 times 10 to the 12 meters per second squared, which is roughly about 200 billion times as much. Tension would be rather flat. All right. So that was actually